Okay, so this week we have 5 problems again, and let's go through them one at a time. And just a reminder, yeah, this I'll be away for a couple of weeks, so after this one, we won't have any problems set for a couple of weeks. Okay, so first problem, um, again, I'm not going to read through the problems, but basically you have a bunch of numbers, n of them, and up to 100. The numbers are between 1 and 200. They're listed in increasing order and there are no duplicates. And what you have to do is to figure out if any numbers are missing from 1 to whatever it is at the end. So you see here, the 9 numbers starts with 2, 4, 5, 7, 8, and so on. And you should know that the missing ones are 1, 3, 6, and 12. And you end at 13 because that's where it ends. And then the second case, they give you 5 numbers. It's all there, 1 through 5. So you say, good job. There are many ways you can do this. You can keep a counter to see what you're supposed to be expecting, right? The first number should be 1, then it will be 2, and 3, and so on. But then when you see something that's bigger than what you expect, then all the numbers before the number you read that you're expecting are missing. And then once you read in 2, then the next number you expect is 3, and so on. That's one way. Another way is to simply have an array of 200 items, because there are 200 of them at most, and just keep track of which ones you have seen and then do another scan to figure out which ones are missing. And for me, I did it the second approach because it was easier for me to think about, even though it takes 2 passes. I only have to keep track of one thing each pass. So it was easier for me to think about. So that's what I'll do. I read in the number of integers. Then I have an array of 200 items, well, 201, but I'm only using 1 to 200, so that's why it's 201. And I initialize them all to false. I've never seen them before. I also remember what is the last number I've seen. And then I just go and read the n integers. All the integers, mark them true, and the last one that I've seen is the last one that I read. And then at the end, I'll do one more pass and I just go through the array from 1 all the way to last, the biggest number that I've read. If I ever see a spot that is not used, then I print that out as a missing number. Okay, and I remember that I have at least one missing numbers, because if I have not found any missing numbers, then I will print good job. Okay, there are other ways you can keep track of that. For example, if the number of elements is exactly the same thing as last, that's also another way to say that you're not missing anything. Because if there's 10 numbers and the last number is 10, then you must have seen all 10 numbers, because they guarantee you that every number is unique and no duplicates. Okay. Anyway, there are other ways you could have done this, but based on what has been done so far, anybody that tried it seems to have gotten it, so I'm not going to spend too much more time on this one. Okay, count doubles. You have an array of n positive integers and m integer m. Count how many contiguous subarrays of exactly m elements have 2 or more even values. Okay, so the size of the arrays can be up to 1,000, and m is less than n, and each number is at most 10 to the 3. You have to count how many contiguous subarrays of m elements have at least 2 even elements. So actually, the first thing that you hopefully realize is that the actual numbers don't matter. The only thing that matters is even or odd. Okay? And I only care about even numbers. So the first thing I'm going to do is I'm going to take my array, and whatever values I get, I'm just going to convert it to even and odd. And because I care about even numbers, not odd, I'm going to make even to be 1 and ought to be 0. Okay, so if the numbers are like, I don't know, 1, 2, 5, 5, 6, 8, 10, I want to convert it to 0, 1, 0, 0, 1, 1, 1, like this. Okay, so I'm going to have an array of 0 and 1, 1 being the even ones, 0s being the odd ones. Okay, and what I want to do is I want to look at windows of size m, whatever m is. So if m is 5, I want to look at all these windows. This is 1, this is another one, this is another one, and so on. There are many of them. And I want to know how many of them have at least 2 ones, because I'm looking for at least 2 even numbers. Now, if you're going to do this the way that we described, so we're going to look at all the windows. How many windows are there? N minus m plus 1. So y plus 1. So if I have, let's say, 10 elements, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this, and m is 5, then the first place can be any of these spots. So let me just, this spot can be what? This spot, this spot, this spot, this spot, and this spot. This is the last spot that can start at window 5, and you can see that there's 6 of them. Okay, so 10 minus m, 5 plus 1 is the number of windows there are. And then each window, if you were to scan how many ones there are, so there's a number of windows times m, because that's how many elements there are. If you do that, then that's n times m minus m plus 1 times m. So let's just call it n times m as an upper bound. And n is actually, m is at most n. So in the worst case, I guess you can say it's like n, m is kind of like n. So it's n squared. Now you might say, well, if m is this big, then actually n minus m plus 1 is small. So if you say m is actually n, then this is actually not many windows. The worst case actually in this, if you want to think about for what value of m is this value the biggest, is actually about n over 2. In that case, when m is about n over 2, the first part is about n over 2, second part is about n over 2, so it's n squared over 4. But if we're talking about big O, then it's n squared anyway. So the main point is, if you do it the usual way, try all windows, where each window scan m steps and ask, is it more than 2 ones? And more than or bigger than or equal to 2 ones? And if so, count that. That would be n squared time. And n, it's 1,000. So actually, that's good enough. N squared is 1. So n is 1,000. N squared is 1,000,000. So even if you do the most obvious way, just to loop through, right? So what do we loop through? So for I equal to 0, I less than n minus m plus 1, I plus plus, that's a starting spot. And then maybe you have something like for j equal to 0, j less than m, j plus plus, and maybe you have something like count. So, okay, hang on. I shouldn't use the word count because that's ambiguous. So let's call it evens, even. And then you say, just say even plus equals to, if this is your a bracket I plus j. And then if even greater than or equal to 2, the final answer is plus plus. That's another one that you count. So that would be good enough. Alternatively, you can actually reduce this to a linear time algorithm using the partial sum trick that we have mentioned once before, or maybe a couple of times before. And the partial sum trick goes like this. So if you want to compute the partial sums, you can just use the partial sum STL function, and I'll show you that in my code. But basically, we'll take this array and produce another array, or maybe you overwrite the entries, where each entry is the sum of the entire array up to that point. So we'll go like this. Every time you see a 1, it increments by 1. Every time you see 0, it keeps the same. And now, if you want to know, so you can do this in linear time. And now, if you want to know what is the window, any particular window, how many ones there are, you don't actually need to scan this whole thing. You can look at this entry, the last entry. That's all the ones up to this point, and minus the entry just before the window. Now, in the case where you start the array, and the entry just before is out of bounds, then you don't do anything, right? So in this case, this window, the first window is 3 ones, and you can see 1, 2, 3 ones. This window, it says that up till this point, the whole array has 7 ones. But I don't want the whole array. I only want this window. So what you have to do is you have to get rid of what comes before this window. So what comes before this window is 4. There are 4 ones up to this point. There's 7 ones at this point. So that means that in this part, there are exactly 3 ones. Okay? And when you slide a window over the next one, 7 minus 5 is 2, and you'll see that the next window has 2 ones, and so on. So the concept of partial sums allows you to quickly figure out a sum of any window in constant time without scanning this window again. And that's the power of partial sum. It turns your quadratic algorithm in this problem into linear time. So I want to show you how I do it in code. Okay, so here it is. The code is actually really short. I read in N and M, right? So that's the first part. Then I have an array. Now, remember that I said, what about, if you have an array and you're looking at the first window, if you all just take, so if the window ends here, if this is the end, let's call it K, then I have to subtract the one that's just before the window, which is here, but the very first window, this window could be out of bounds. So what I do is I actually, instead of using exactly n elements, I'm going to use one more, n plus 1. I'm going to put my real data here, and then I'm going to put 0 here. The reason I put a 0 here is that when I do this trick, it will always just subtract a 0. I don't have to worry about doing special case out of bounds. So that's a little trick that I allocate 1 extra element to avoid checking for out of bounds. Other than that, it's pretty much what I said. You read 1 to n. Okay, so this for loop is a little bit different because I'm going from 1 to n instead of 0 to n minus 1. I read it in, and this converts. Okay, so what does it do? If x is even, x mod x percent 2 is going to be 0. 1 minus 0 is going to be 1. So even becomes 1. If it's odd, remember these numbers are positive. The problem statements say that's a positive numbers when you do percent 2. If it's odd, it gives you 1, and 1 minus 1 is 0. So we'll turn even into 1s and odd into 0, which is what I was hoping, what I was trying to do. Then this next line just turn the array into the partial sum. So the first 2 arguments says what is the input array, and the third argument says what is the beginning of the array that you want to write back to. And in this case, I'm just overwriting my original array. If you want a vector, if you want to have a separate array, a vector, you can allocate a separate array of n plus 1 things and then use the other array of vector. Okay, anyway, now that I've computed partial sum in A, then I just count, right? So for I from M to, let's say you could n, so these are all the possible places that n's a window. M is the first one, the first place or the place where the first window ends, and n is the place where the last window ends. And if, the partial sum entry, right? If I'm looking at this window, whatever this window is, this is I look at this partial sum entry minus the one just before it. And if that's bigger than or equal to 2, that means I have at least 2 even numbers. That's when I increment the number of such intervals, such windows. And then at the end, I just print out the answer. So notice that, yeah, it's you have to use partial sum, but this turns a quadratic algorithm into a linear time algorithm. In this problem, the problem's small enough that maybe you don't really care, but it's still a useful technique to know. Okay. All right. So that's counting doubles. Let's see. Judging trouble. Okay, so you have two judging system, and they both have n different results. So n can be up to 10 to the 5, 100,000. N results from one judge in arbitrary order, and then followed by n results by the other judge. I'll put one line with the maximum number of judging results that could have been the same for both systems. Okay, so basically, I don't really care about what these words are, so I'm just going to call them A, B, C, D, E. So on the judge one, maybe you have a bunch of A's, B, A, C, C, B. Maybe you have something like this. Maybe you have a D, I don't know. And then judge two, maybe you have B, D, C, C, B, D, D, like this. How many of them? 1, 2, 3, 4, 5, 6, 7. I need 2 more. So maybe you have something that never seen before, and then you have something else that's just like 8. Okay, so how many of them could be consistent with each other? Well, clearly, E can never be consistent with each other because there's no E anywhere, no E on the other side. So that cannot be. And so you only look for things that are in common, and you look at A's, right? So let's look at A's. A can only be consistent with A's on the other side. It can never be more, A can never be consistent with C or whatever else. So this means that you can actually just look at each letter or each kind of judgment separately and then add them up. And you have 4 A's here, but you only have 1 A. So how many of these A's can be consistent with each other? At most 1. So hopefully what I'm trying to tell you is that you basically just count up how many of each type of things there are. Okay, so am I missing something? 1, 2 B's. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and for each letter you match and say, then take the minimum, right? Those are the maximum you can possibly match. And then here, one of them has 1D and the other has 3D, so at most one is consistent. And if you want, you can say 0E. So all you have to do is match, basically count how many times A appears on one and how many times it appears on the other, take the minimum, and try to do that for every single judgment. Now, these are not just A, B, C, D, they are actual strings. So you need a way to keep track of how many times a string occurs. And the easiest way to do this is using a map, where the key, that's called frequency, the key is the problem, the judgment, and the value is the count. And what you do is you just basically sum them all up, right? For each set of judgments, you look at the string, increment it, the frequency for that string. Once you collected this data, then you can just look them up for both and then find a matching one or the other one and take the minimum. So here's my solution. Again, it's fairly short. Read in N. And I'm going to have two maps. So I'm using an array of maps, so it's easier for me to index. I can write a loop that goes through the problem set, the judgment twice, right? So I do it twice. For each one, I go through N times, read the string, and then frequency K, K is the problem set 0, 1. And then S is the string that I just got, plus that makes me realize that I have one more of that string. And now what I'm going to do is I'm going to match them up. Now I actually only have to go through one of the frequencies, and then I will look up at the other one to see how many times it occurs. It could be 0, okay? And that's okay, because when you take the minimum, 0 will be 0. So here it is. Answer is my running total. I looped through the first map of the first problem set. And this is a way, remember that in a map, each entry comes as key and value. And the way to automatically pick it apart, it's like this. It's in C++, you can use auto, square bracket, S and C. S would be the string, C would be the value. So go through all the first map, and then for each one, I go to the second map and look up that string. If that string is there, it will return the value, return whatever count it is. If it's not there, it will create an entry and return 0, which is just fine. So I'm not going to bother asking if it's there or not. I'm just going to make use of the fact that if it's not there, it's going to return 0. And then I'm going to take the minimum of the value in map 1 and the value in map 2. Whatever that is, I add it to the running total, and that's the answer. Okay, so this is mostly an exercise in data structures to help you look things up quicker. If you try to do this yourself without using any data structure, this is probably not going to work, because the number of judgment is up to 100,000. And if you don't use anything that's n log n or better, if you use any kind of algorithm data structure that's n squared time to process n queries, then it's going to be too slow. Okay, 100,000 squares, way too much. Okay. Evening out. This has a fairly short problem statement. It also has a fairly short solution, but you have to know what's going on, as usual. You have two integers a and b. You want a to be divisible by b. You can either increase or decrease a by 1. What is the minimum the coins she must pay? The first and only line contains the two integers a and b. They're both at least 1, so that's good. Otherwise, you have to worry about division by 0 or negative numbers. And up to 10 to the 18. Now, immediately, that should give you a little bit of a alarm bell, because normal 32-bit integers, if you just use an int, it goes up to 2 times, it's about 2 billion. Okay, so about 2 times 10 to the 9. So 10 to 18 is too much. And we need to use the 64-bit integers. So it's 10 to 18 is okay for a 64-bit integer. So that's the first thing. The second thing is, can we figure out how to do this? Right? So if you take a number and you divide by b and the remainder is 0, then you're done, right? Nothing to do. The answer is 0, right? You're already divisible, we don't have to do anything. If the remainder is something, let's just pick some numbers. So hopefully you'll see the pattern. Let's say you try to divide by 3. The remainder, of course, is 1. So that tells you that if you subtract 1, then you get, instead of 10, you get 9, and 9 is divisible by 3. But there's another way you can get to a multiple of 3. You can either subtract or you can add. You can add what? You can add 2, right? The next multiple of 3 is 12. How do we get this 2? The remainder here, 2, it's the b, the divisor, minus the remainder. So basically, the answer, it's either to decrease r or increase b minus r. Those are the only two choices. And it will work even in this case when r is 0, because if you just take the minimum of these two things, if one of them is 0, then of course you're going to take the 0 anyway. And I guess that's it. You read the integers a and b, you compute the remainder r, and you either take r or b minus r. You just have to make sure that you use 64-bit integers, which it's long or in 64, in 64T. So you can either use long the way I do it, or you can use int 64. Wait, hang on. Int 64 underscore t. I guess int 64 underscore t is a little bit more portable, but long is also acceptable these days. Okay, so this is I don't know if I call it number theory problem, but it's a relatively simple one if you think about it. So I want people to start thinking about numbers, divisors, remainders, and then how things interact with each other. So keep that in mind when you see problems like this. Okay, the last one is a little bit of a challenge problem, I guess. So let's have a look. Okay, a sequence of positive rational number can be defined like this. You start with the roots as 1 over 1. Then whatever the root is, or whatever the node is, the left child of p over q, it's p divided by p plus q. And the right child is p plus q over q. It looks like this. And then you can look at this one level at a time. First level is 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So write a program which finds a value of n for which f of n is p over q for inputs p and q. So basically, you are going to be given p and q somewhere in this tree. You have to figure out what numbering it is, how many levels there are, and all that stuff. You have up to 1,000 cases. Each one has the numerator, denominator, and a slash, follow, and so on. And then for each data set, there's a single line of output. It contains the data set number followed by single space, which is then followed by the value of n. So this number in a sequence. The input will be chosen so that n will fit inside a 32-bit integer. So they tell you that you don't have to worry about using 64-bit integers. Okay, so that's what it looks like. Now, how do you tackle something like this? Right? first thing you probably have to, realize is that whatever P and Q they give you, you have to figure out where you are in the tree. Are you in third level, fifth level, or whatever? But you also need to know the path to get you there. And perhaps what we want to do when they give you a node, you want to figure out how to get back to the root. Okay? And that turns out to be the key. So if you are in a node, then the left child, it's P divided by P plus Q. And the right child is Q, so P plus Q divided by Q, like this. Now, if you think about it, P is always less than P plus Q, so this is always less than 1. And P plus Q over Q, P plus Q is always bigger than Q, so the numerator is always bigger than the denominator, so this is always bigger than 1. So whatever number they give you, if it is less than 1, so if the numerator is less than the denominator, you know that you're left child of somebody. So given P and Q, if P is less than Q, you are a left child. And if P is greater than Q, you are a right child. What if they're the same? Well, if P is the same as Q, then you're at the root, because the root starts at 1 over 1, and you're done. Okay, so now how do you get the parent? Because if you're here, we want to walk up the tree to figure out how to get to the root. We'll explain why you want to do that. Well, if you're left child, if you're given P and Q, now I know that there's a little bit of confusion here because this P and this Q are not the same as these P and Q, okay? Because I'm talking about P and Q being the child here. To get to the parent, the numerator hasn't changed, so it's still P, but the denominator, it's the denominator minus the numerator. Okay, when you take P plus Q minus P, you get Q back. So if you are a left child, you want to get to your parent, this is how you do it. And if you're right child, same argument, or similar argument, I guess. Q doesn't change, but the top, it's going to be P minus Q. Okay, so this is how you get to the parent. Wherever you are, you get to a parent. So what we're going to do is we're basically going to walk up to the parent somehow, and then maybe that will help me. Why does that help me? Now, if you've learned about this thing called binary heaps or priority queues, you may have seen something that's very similar. You have a complete binary tree. Okay, exactly how the numbers are filled out doesn't really matter in terms of what's in the nodes. And you label things, 0, 1, 2, 3, 4, 5, 6 in one level at a time, and so on. And in that case, whatever node you're in, you have rules. So left child, it's 2x plus 1. Right child, it's 2x plus 2. And then the parent, it's like x minus 1 divided by 2 rounded down. And I'm talking about not what's in the node, but what are the numbers. And what you're looking for actually is almost the same thing, right? You're looking at the numbers, except that the numbers you're looking for doesn't start with 0, but starts with a 1. Okay, so there are a number of ways you can handle this. You can either convert all the numbers from 0 to and so on, and then adjust things before and after the calculations. So you could, for example, just compute the answer using what you know with the binary heap with these formulas, and then at the end you add 1 to the answer you got. Or you can work out a similar formula, and if you work it out, you'll realize the left child is 2x and right child is 2x plus 1. You can see that this is true everywhere in there. We don't actually care about parent, I guess. Okay, so what am I going to do? How am I going to use this information to help me solve the problem? Okay. What I'm going to do is I'm going to do the following. I have a tree, and I have a node somewhere. This is P and Q that I'm given. I can tell one of these three cases, right? A, B, and C. Three cases. If I'm case C, I'm done. So case C means that I'm at the root. I must be 1 over 1, so the answer is 1. That's it. So the answer is 1. That's the easy case. What if I'm not case C? Well, then either I'm a left child or I'm a right child. In either case, I can figure out, right? So this is left child and right child. I can figure out who my parent is using these formulas. And I'm going to recursively ask, what is the number here? So recurse and ask f of parent. Let's call f the number for that node. So f of parent, because I know that whatever it is, my answer is, so if the parent is x, my answer is 2x if I'm a left child, or 2x plus 1 if I'm a right child. So all I have to do is to figure out my parent, recursively ask, what is my parent's number? And then either 2 times x or 2 times x plus 1. Okay, and whenever you have a regular binary tree and you're looking at labeling nodes one level at a time, it always goes like this. There's this pattern that you can use. 2 times x to get your left child, 2 times x plus 1 to get your right child. If you're using 1 base, if you're using 0 base, then it's 2 times x plus 1 and 2 times x plus 2. Either way, you can work that out. And the code, again, looks deceptively simple. Okay, so here, this part just, read in the P cases, and then for each case, read in the input, and then call solve PQ. So solve PQ is the one that does everything. What does it do? Check if it's a base case. If P and Q are both 1, or they're the same, but it doesn't matter because they tell you that things are always reduced. So you're done. That's your base case. If P and Q are both 1, you're at the root, it's 1. Otherwise, if P is less than Q, you know that you're a left child. So you recursively go to the parent, okay, and then take the answer times 2. And if you're right, if you're on the right branch, you're a right child, then this is your parent. Recursively, you ask what the number is, multiplied by 2 plus 1. So this, again, this problem, like most of the problems I chose this week, are easy and short to write in terms of coding, but it takes a lot of insight to get there. Okay, and as usual, you can see all my submission on GitHub. We're gonna take a couple of weeks break while I'm gone, and if you have any questions or anything, you can always ask me on Discord. Otherwise, I'll post more problems in a couple of weeks. Okay, see you guys later.